First of all, I would like to thank the organized committee for inviting me to give this talk in this symposium. I plan to talk in Russian, but probably in English will be better. Andrei asked me that English is very important, and I will try to present in English, but my English practice was limited last time. But anyway, I will try to present this result. Okay, the content of this report includes such sections. At the beginning, in the introduction, I will say about motivation of this work, why we do this research, and then step by step, I will say about some basic issues about pulse theorem and derivation of this theory in waveguide, application of this theorem for Rosa protocol, why it is interesting to apply this method, also I explain, and then also I present our first experimental results in such system and some discussion. Okay. So at the beginning, why we need to do this? We started our research in optical quantum memory by using usual scheme when we realized interaction of light with crystal, and we tried to find optimal conditions for realization of quantum memory to increase its efficiency, fidelity, and so on. But last 10 years, it was recognized that using some integral technologies very important to develop quantum memory, and there are two main ways. One way it's using some waveguides, and another some resonators. And in this talk, I will say about using some waveguides. Here also we have a lot of directions and the possible realization of waveguides on the surface, volume, in different platform. And in our work, we performed experimental study, derived interesting, very important equations for pulse area, and solution of these equations give us prediction of 2 pi solitons, which was observed later, and so it was starting point for optical solitons. And what is later, you can find some papers, and until now, you see that pulse area, it is still important issue which is studied and in different system, in 2-level, not only in 2-level and 3-level system, and now we see that principally it's possible to apply for studies very general nonlinear properties of interaction between resonant light and atomic system. And also we found that it is a very useful tool for studies of optical photon echo and photon echo quantum memory scheme. What does it mean, photon echo? Maybe just shortly, we have two pulse interaction in such system, and because of action of second pulse, it's possible to rephase atomic coherence, which was excited by the first pulse, and after some time, T2, this polarization is recovered, and we see echo signal. And this technique, echo technique, now is very useful technique in many applications, in particular in spectroscopy. Principally, we can say that at the beginning, we began to study coherent non-stationary spectroscopy. There are stationary spectroscopy and non-stationary spectroscopy. And principally, quantum memory, it is some continuation of such non-stationary coherent spectroscopy. Because of this, maybe we began to study quantum memory. And also, I would like to A little bit later, Kapilin and Negibarov found that photon spin echo also can be realized in optics, and Bella Koenig-Hartmann, this group independently observed this effect in Rabi crystal, and I can say that Kapilin and Negibarov worked in our institute, in Physical Technical Institute, and after that time, this work initiated a lot of research in Physical Technical Institute, and also we started this. And a little bit later, Han applied pulse area to photon echo in such scheme when two pulses was launched to the medium along the same way, and he studied pulse area of all echo signal, and it's very nice that pulse area approach give us opportunity to find total pulse area which are excited after two pulses. And analytically, he found this scientist found solution for total pulse area, and you can find this picture in book Ali Neberly, Two-Level Atoms and Optical Resonance. Yes. But from that time, it was unclear what will be the properties of each particular pulses. And so a little bit recently, we studied in detail that principally it's possible to find pulse area of each pulses. We here I can say that now we have some papers which applied to photon echo to study pulse area of echo signals, and in particular, last paper is devoted to studies such system, such multiply secondary photon echoes in waveguide. In a recent paper. So I can say that in this work, we derived the pulse area theorem for each echo pulses, first, second, and so on, and found some analytical solution. In recent paper, we found pulse area of each of the pulses, first, second, third, and so on, and we reproduced by such method result of Mark-Cole-Han, and you see that principally we obtain the same results for total pulse area by calculating individually each pulse area. After this, for us, it was very interesting result, which was not solved more than 40 years from that time. And we decided to apply this technique to formation of pulse area in the cavity. And also we applied this technique and by using a little bit different equations for pulse area in the cavities, and found solution for few echo pulses after excitation. And here you can find some pulse area of first echo pulses, second, third, and so on and so on. And here recently such effects, multiple echo signals in microwave resonator, also studied theoretically and experimentally in microwave resonators, and we say that our results are consistent in good agreement with these calculations, which don't use possibilities which we found in pulse area technique. But now we, as I said, we're interested in integrating optics in waveguide and so on. And just I will show you some list of papers to studies of incoherent interaction of light with multi-atomic ensembles. And here, exactly these papers devoted to quantum memory in waveguides. Some particular papers. So principally, but in spite of such number of papers, there are no general theory which could explain interaction of light precisely in waveguides, and in particular, general properties of photon echo in waveguide. Because of this, we found that it's necessary to go from the starting point and to derived equations for light and atom in waveguides. And in our system, our colleagues from Moscow State University, Sergey Pavlovich Kulik and Alexander Kalinkin, they created a waveguide in crystal with some parameters, and we numerically studied properties of this waveguide. We found that this waveguide has single mode optical wave, single mode, and for single mode waveguides, it's possible to start from this equation, from this Hamiltonian, where this Hamiltonian of light, single mode light, and atomic ensemble, interaction of them, and this coupling constant, which is determined by the special structure of light. This is waveguide membrane function. So principally, it's possible to include all the properties of the waveguide into this system of equations. And after some very typical calculations, it's possible to obtain Maxwell-Bloch equations for amplitude of light and Bloch vectors. And here we should take into account some Rabi frequencies which determined by the membrane function. And after some calculations, principally it's possible, and we found such equation for the, it is not pulsary, but some envelope, integration under the envelope of the light, which has such form, which is a little bit different from the pulsary of McCall-Hahn. And in particular case, when we have only one atomic groups, this just one with one orientation of dipole moment, this equation is a little bit more simpler. And what is nice is that there is analytical solution of these equations. And red line show us the evolution of pulsary in the waveguide, and we see a very big difference with respect to behavior of McCall theorem. McCall theorem, it is related to these black lines, and we see that splitting point when initial pulsary larger than pi, we have in McCall-Hahn theorem predict 2 pi soliton, but in our case, stable 2 pi pulses can be created only if initial pulsary larger than 2 pi or larger than 4 pi. This is a very big difference. But principally, it's nice that this is analytical solution. And we found it for Gaussian mode, but it's very well known that usually, very often we have Bessel mode. Zero order Bessel mode, this typical single mode for single mode cavity case. And in this situation, what is interesting that this function, instead of this function for Bessel function, we have very similar behavior. That principally we see that that Bessel function has the same qualitative properties. That principally no big difference. That we will have the same behavior of pulsary even we have Bessel function. And also I can say that the same behavior will be for transmon, for surface plasmon field, but I will not talk about this. Okay. Next step was to apply this technique for pulse area of echo pulses, and similar to previous work, we derived all these equations and found pulse area of first pulse and this second pulse, sorry, second pulse, first, second pulse. And for second pulse, these equations will be like this equation. And from this, it's possible to find that if first pulse area decrease, second also will decrease to 0 if its pulse area initially smaller than 2 pi. In this case, we can find that we can find similar to approach of Mark-Kolhan pulse area of all echo pulses. So this is first pulse, second pulse, and this is pulse area of all multiply primary and all echo signals. And using pulse area of in waveguide from these equations, we found that total pulse area of all echo signals also can go to the to 2 pi at some initial conditions. So this is principally total perfect solution. Okay, but of course we are interested in particular each echo signal, primary and others. For this situation also it's possible to get such equation for echo signal, but here it is more complicated, but principally numerically it can be easily solved, I hope. And now we are working on this direction, and principally we can say that such equations can be applied for different scheme of photon echo, for different scheme, which now are under consideration. And in this work, we focus to the ROSA protocol, which presents such scheme of excitation. When we have initial pulse, usually it is single photon level pulse, very weak, and then we apply 2 pi pulses. And experimentally, if all pulses propagate in a long direction, one direction and opposite direction, these pulses should be propagated in opposite direction in order to exclude some noises, and echo signal propagate in forward direction. And why this equation, this ROSA protocol is some kind of extension of primary echo signal. And principally echo signal in ROSA protocol, this is just this echo which is rephased after second pi pulses. So this is a very simple generalization of this technique. So principally experimentally it is very nice, very simple for realization, but really it is there are so many problems which we need to solve in order to realize very high efficiency and to suppress quantum noise. Anyway, we go in this direction, and principally it's possible to find exact equation for pulse area. This is some kind of calculations, but you see analytically, of course, it's possible to solve, but for numerical calculations, I think it is not problem. And now we go to our experiment, and this is our experimental setup. This is cryostat. Signal fields propagate in this direction. This is control field in opposite direction. This is crystal at helium temperature. And this cryostat, of course, we have some lasers and detectors, all techniques which it is necessary to apply for this experimental scheme, and more additional information about our waveguide, that we have this waveguide in crystal with thulium. This is exactly very nice material. Also, it's promising for quantum memory, but we need still to improve efficiency and to suppress quantum noise. This is two main problems in our task. And in order to provide very good pi pulses, we use pulses with chirped frequency. You see, this is frequency changed during the excitation inside of this spectral domain. and we observe experimentally that principally pi pulses in this case will be much more better to realize within this spectral range, and the efficiency in this case of quantum memory increased 1 order of magnitude. And this is some parameters, but we can say that creation of waveguide now is not so ideal because some additional losses are created in this waveguide. But principally, now this technique is developed, and we hope that in the future, in near future, this waveguide will be better. And this is our experimental results. Because we used optically thin medium, efficiency was quite low, about close to 1%, a little bit lower. And this is very interesting two curves. This is behavior of intensity of Rosa echo protocol. So we changed intensity and detected efficiency, intensity of Rosa echo. And depending on the intensity of control fields, we also measure coherence time. We see that T2 decrease with the intensity of control fields, and it indicates that principally we have some maybe instant spectral diffusion or some kind of diffusion, Okay. In this, for such situation, we derived equation for pulse area. Of course, you see now it is quite complicated because we should take into account special profile of the pulses, chirping of the pulses, and so many parameters include in our this amplitude of echo signal. And I would like to know that in our system, maximum efficiency will be like this for ideal pi pulses. But we, of course, get a little bit lower efficiency. And in this case, here I reproduce just our preliminary theoretical results, comparison of theory with experiments. We see that if we ignore any relaxation, we have three curves. Theoretical curves, which very close with parameters close to experiment. And what we cannot explain that very fast, very steep increase of intensity of echo pulses with intensity of control fields. So we see that we need to take into account relaxation, phase relaxation. And now we are taking into account we will study two type of diffusion, instant spectral diffusion and resonant dipole interaction, and preliminary theoretical calculations, theoretical results give us such information that principally we see that we can explain very fast, very steep increase of intensity by taking into account diffusion, spectral diffusion. But these questions still under consideration. That I conclude that pulse area, we derived pulse area theorem in waveguide. We applied also, we derived these equations for pulse area for photon echo also. It was, we formulate pulse area in waveguide for echo. We applied this technique for Rosa protocol, and we realized first experiment in waveguide for Rosa protocol. And finally, I can say that why, again, we use pulse area for this technique. It's very easy to check. Is it possible apply or not? If if shape of echo pulses coincide with shape of exciting pulses, pulse area provide us almost 100% information about all this process. So it is very simple way to study general nonlinear properties of echo signal in this technique. This is our team, except Kalinkin and Alexander Kalinkin and Sergey Pavlovich Kulip. And thank you for your attention.
Thank you, Sergey, for your talk. We have a couple of minutes for questions, please.
May I ask a question?
Okay, Maria Nikolaevna, please.
Sergey Andreevich, thank you for an interesting talk. And the question is, you considered a single mode waveguide. Do you mean 0-0 mode, or the results can be also for higher order modes? It's the first question. And the second one, do your results depend on the shape of the cross-section of the waveguide?
Thank you for these really important questions. General equations for pulse area include arbitrary mode function. Principally, it's possible to use for single mode, two mode, many modes. But analytical solution I found for Gaussian mode, for Bessel mode, for other mode, for exponential mode. If we have more complicated mode function, principally equation exists, but analysis will be more complicated. And first question, simple, but I can say that Gaussian mode and Bessel mode is very typical mode. It is very typical, or it is principally it's possible to apply in many situations. I discussed this issue with some experimentalists. They said that this is practical point.
Thank you.
Извините, но вопрос будет на русском. Правильно ли я понимаю, что площадь импульса соответствует энергии всего импульса? Вы хотите узнать именно энергию импульса?
If I can say that principally it's possible to perform experiment when we measure pulse area. Also, it's possible to make such experiment by using homodynamic detection, for example. Principally, this theory is applicable for arbitrary situation. But if you measure intensity, if you would like to connect experiment with intensity with the theory, it is important to have situation when temporal shape of the pulses, input pulses and echo pulses are the same temporal shape. For example, if you have very broadened in homogeneous broadening, very broadened in comparison with spectral width of the pulses, this situation takes place. In this case, that square of pulse area will give us directly information about intensity.
Okay, thank you. Andrei, do you have a question?
Sergey, thank you for interesting talk. Just for my education, you told about scheme for almost single photon echo. Is it possible already realize such experimental research? Yes.
And
you do this
experiment really. For example, recently we published paper when input signal was 5 photon in average.
Okay.
In optics.
Okay, but okay, 5, but single.
It's possible for singular as well, but it's need to more time for averaging. Yeah. But quantum noise will be. It was a large quantum noise. Quantum noise was about 5 photon at that time. Because of this, it was no any reason to use. Because of this, we need to suppress quantum noise further in optics. Recently, in microwave technique, I will just shortly say, we realized quantum memory for pulses with average just 1 photon, even smaller, 0.5. If quantum noise is very low.
Okay, thank you.
Thank you. We actually have noted, but very short, just one short question. How do you define pulse area for inhomogeneous profile of waveguide mode? For the central point, for other points. So you have some profile of waveguide mode. Yes. For which point you define pulse area?
Okay. Yes, for central point.
For central point. So for other modes.
In equation, we have, if we have just atoms with one type of atom, very simple equations. It is exactly for central point equation.
Okay, okay. Thank you.